Bad outside. Mm-hmm. Yes, indeed. Okay. So let me pull up where we are. Folks still coming out. Almost everybody's in right now. So, well, the important thing is we're all safe and we're all doing okay because there was a lot of damage. A couple of people did lose their lives. Okay. So, where you should be in Canvas, we were talking about measuring energy flow. So we're going to quickly review um, all of these definitions, and then we're going to move on to still how energy is cycled through different what we call biochemical cycles. All right, I'm gonna give it another few minutes and then because technically we're 5 minutes in, and I do like to get started 5 minutes in. So if you are what you need to do is log into Canvas. I want to go through the vocabulary. I was doing an assignment with another class, and I need to clarify, I found I need to clarify producers. So I'm going to do that with you all first and then allow you to read the next section. So read this part over while we're waiting next few minutes. The module's name is Measuring Energy Flow. It's in the section EFE. All right, so again, we're going to review this part because we left off talking about this part. But like I said, in one of the activities, might not have been your class, but another class, the understanding of producers and being able to pull out a food chain within a food web was not clear in the answers that were given. So I want to make sure you have a clear understanding of that. And then on Wednesday, we will have a short activity where you have to actually examine the food web and pull out. Let me stop sharing for a minute and make sure that it wasn't this class. Because my comment on everybody's activity was you're not identifying the no, it wasn't this class. All right, so I will assign it to you on Wednesday, and I want you to be clear um, as to how to do this. All right, so let me come back. Okay. Actually, if you just make sure that you read that page over while I do attendance and set up GoGuardian, and then I'll come back. But study the food pyramid, study the picture of the food web, and read all the definitions, and I'll be right back with you shortly. I'm going to go ahead and do attendance, turn on GoGuardian. All right, so if you're not where you're supposed to be, because everybody should be looking at the page in Canvas. GoGuardian is on, and I'm looking at me. Everybody should be on the page in Canvas. Energy flow. I should be looking at energy pyramids on everybody's page. I wonder why Jaquise isn't here. He logged into my last class, so he's early for that class. Now he's not here for this one. Okay. Let me quickly do
Where's the
attendance.
page again?
Hello.
Is it called energy consumption module?
Measuring energy, yes, the EFE module, and you're looking for the one that says measuring energy flow.
Okay.
All right. And as soon as I mark these folks absent, I'll be right with you. Mm-mm. Yes, you can watch the video on your own. So yes, how can you measure energy is what you should be looking at the video. Is the flow of energy and matter through an ecosystem. So go ahead and look at that because you'll have trouble hearing it when I play it. So go ahead and watch that on your own. Okay. Some late students in a minute. There they go. Okay. All right. Hello, gentlemen. Somebody I'm missing. Mm, mm. Okay, I found my missing person. All right, so everybody go ahead and watch this video on your own so that you can hear it, and then I'll talk about it in a minute. There's a couple of things that need to, and again, it's the um, energy, measuring energy flow. Mm, that's right, I forgot. Y'all can see when I'm looking at you. All right, everybody should be here. All right, I'm going to start from right here. So if you're watching the video, pause it for a minute. All right, so we're talking about feeding levels, trophic levels, and those are feeding levels. And the and we're also talking about energy. Okay, we're talking about energy. How does energy flow? We get our energy by the foods that we eat. And there are levels of feeding. So the first level, and like I said, this is a review, trying to go back and review. First level are producers. And there, if you're looking at a food chain and you're looking at a picture, they're always going to be the first one. They're always going to be at the bottom. And producers are always plants. You cannot. So if you are if someone asks you, and you will be asked on Wednesday to write or identify the food chains in a food web, you always want to find where the plant is first. And in different environments, it may not look like a plant like this one. If it's an aquatic environment, it might be algae. It might be what we call um, phytoplankton. There's two kinds of plankton, zooplankton and phytoplankton. The zooplankton are the animals like zoo. So you think of the zoo, think of animals, and the phytoplankton, think plants. Those are going to be your microscopic plant organisms for those organisms that feed on microscopic organisms. Right? But you always start, whatever ecosystem you're in, you always start with the producers. They are the only ones that can capture the sun's energy. And we can't do it. We have to get our energy from the things we eat. Plants make their own food. Once they capture the energy from the sun, they take the carbon dioxide from the air and the water from the soil, and they create their food product, which is glucose. So they make their own food. Then they use the food that they make in order to carry out all of their metabolic activities. So then the next level is your prime. So we have different levels of consumer. Everybody else is a consumer. So you really have two things, producers and consumers, but you have different kinds of consumers. You have the consumer that eats the plant. They are the primary consumers. Okay. Then you have the organism that eats the primary consumer. They're the secondary consumer. And then we have tertiary and quaternary consumers. Sometimes the quaternary one is called the apex consumer because nobody eats them except decomposers. Okay. So this is a food chain. But as they point out, in society, things don't eat one kind of thing. Even you don't eat one kind of thing. You eat a variety of things. So if the grocery store was out of your favorite food one day, you wouldn't starve because you just find something else to eat. That's what happens in nature as well. So this is where we get to look at a food web. So again, if you look at the food web, the bottom of this food web, even though there's different things going on, the bottom of it is always a plant. So you have a tree on one, you have grass on another one, you have a shrub on the other. It is the first thing in the food web is always the producer. And then our arrows point in the direction of energy flow. So again, the conversation is about energy flow. It goes from the thing that is eaten to the thing that eats it. So which way you draw the arrows makes a difference. It tells the direction of energy flow. That's a test question. What do the arrows represent? They represent energy flow. Okay. All right. Our consumers have different names as well. So our primary consumer eats plants, so they are a herbivore. So again, there's a lot of vocabulary with this, so make sure you're keeping up with your vocabulary. There So herbivores are the plant eaters, and next you have the carnivores. The carnivores are meat eaters, and they consume the plant eaters. And then there are different kinds. After that, we have omnivores. Omnivores eat both plants and animals. So that's not here in the paragraph, but those that eat plants and animals. So you might be given a picture like this and then ask which one of these organisms is an omnivore. So you would need to follow the arrows to figure out which one is eating both plants and animals. Quickly look at this picture and tell me Is there an omnivore in this picture? Somebody, you can type it in the chat. Look at the picture and tell me, is there an omnivore, something that eats both plants and animals? And to be honest with you, I don't see one in this one. Now, what is missing in this picture is the decomposers. And the decomposers are at every level. Okay, decomposers are, because all of these things are going to die. The plants die, the grasshopper dies, the giraffe dies, everything is going to die, and decomposers will feed off of them. Okay, so technically, decomposers are also consumers. They don't make their own food, they feed off of dead things. So they are consumers. Okay, all right, moving right along. All right, we're going to look at energy flow. This is important. Write this one down if you're taking notes somewhere. Energy flow decreases as you go up the pyramid. They lose it, and it's called the 10% rule. So the plants may have one consume 100% of the sun's energy, and then it uses 90% of it. So if you eat a plant, you're only getting 10% of the stored energy. All right. And then the herbivore eats the plant and it takes in that 10% and it uses 90% of what it just took in and it only stores 10%. So, and then the same thing with the next level, when the carnivore eats the herbivore, it's only focusing on 10% of the stored energy in the herbivore. So it's only receiving a fraction of the energy that the plant made in the first place. So as we go up the energy pyramid, and do we have a pyramid? Let's look at this. All right, here we go. This is what I'm referring to. All right, draw a picture of this pyramid and with the numbers that you see on the side, because this is important. So in your notes, draw a picture of this pyramid, and then we're going to talk about this 10% rule. So if you notice at the bottom, the primary consumers are 100%. And if you lose 10% of that, and I always say just move the decimal point. So if you're doing it by percentage, just move the decimal point. So notice this, the primary consumers only have 10% to offer. Then you move the decimal point again, and the secondary consumers get 1% of the original 100. And then you move the decimal point again. And the third level consumers are getting 1/10 of the original. And the apex predators are getting 1/100th of the original energy. So again, it's important that you draw this because you need to know how much, and because that's a typical environmental science question, how much energy is lost in each level. And they may give you a picture like this, and they may give you a number. And then if they say if this level has this amount of energy, how much is the next level actually going to have? Okay. And you need to know that each level is going to, and some of the energy is lost to heat because, like, for example, your body is generating heat right now. You had breakfast, and some of the energy is used for your metabolic processes to keep you awake, hopefully during class, and some of it is lost to the environment. Okay. And it says lost, but it's being utilized in the environment. Remember, we live in and we're going to talk about energy cycles in a minute. Nothing is lost. The law of conservation said nothing is lost. The other thing you need to remember as part of your diagram Let me move this up a little bit. So your diagram should be like this. You should title it Energy Pyramid. Make sure you have a sun in your diagram because the original source of energy is the sun. Okay. And again, this is called the 10% rule, where the available energy for each and trophic level is 10% of what it was for the original. And it's not that it's lost, it's that the organism on that level is using that energy that it ate. Okay. And it needs 90% of the energy that you take in, you use for all of your body processes. If you don't use it, you store it. But what they're saying in general, 10% is only available for the next organism. So that stored energy is available for the thing that is eating you or eating that organism. Nobody eats you all. We are the apex predators. Hopefully. All right. The other thing you need to understand what it says about biomass. Biomass is referring to the level that has um, the most living things. So the base is, we use the triangle. So this shows the base. The base is wide because it has the most biomass. And there's less and less biomass as we go up the pyramid. All right, so I'm going to close that, but you probably have yours open even if I close mine. All right, and it talked about the numbers. Again, we use a pyramid because they're to represent the number of organisms. So in a terrestrial ecosystem, we're talking about grass and grasshoppers and mice and snakes. But it's different in aquatic ecosystem. It would be different in a desert ecosystem. You wouldn't have grass in a desert ecosystem. You might have cactus. So you always have to look at what would be the example of what ecosystem are you looking at and what would be the example of your producers. It doesn't matter what ecosystem you're looking at, it's still going to start with a producer, and they will be the widest thing in your energy pyramid. All right, then there's that word biomass. Okay, looking at the same terrestrial ecosystem, notice the numbers. There are far more uh, blades of grass in a terrestrial ecosystem than there are grasshoppers. Okay, and later on we'll look at, so if we were to take out the mice, if for some reason the mice got a disease and they died, the snakes would also die out because they're only eating the mice. But the grasshoppers will overrun because nobody's eating the grasshoppers. But if there are more grasshoppers and they feed on the grass, eventually they can eat up all the grass. So we look at the effect of taking an organism out of the pyramid or the food chain and the effect it has on everything else. Okay. All right. Looking at, I don't know if I need to, hopefully everybody got a chance to watch, where'd it go? The video. I kind of skipped over the video. And this one shows you, again, energy flow. Just looking at the diagram, that the tree is your producer, the rabbit is your herbivore, it eats plants. Then you have whatever that is, it looks like it could be a mouse or something like that. That's not labeled, but those are the herbivores. Then you have your carnivore, which eats the rabbit and the mouse or the squirrel. That looks like it's a squirrel. but notice each one of those heat is given off. The tree gives off heat. The herbivores give off heat. The carnivores give off heat. And then also notice that the arrows also point down to mushrooms or decomposers. They feed off of decayed material. Okay, so understand the names and which way the energy is flowing, and the fact that heat is given off on each level. All right. Let me, I don't know what that, it should start over. Let's start over. Start over. Okay. Take a minute to, mine is already done. Yes, they were. Andre said dinosaurs were apex predators. Yes, they were. The theory is the only thing that took them out was the change in the atmosphere. That's one of the theories, is the atmosphere change, and they could not breathe anymore in the changing atmosphere. And that and a meteor. There were two cataclysmic theories on why the dinosaurs became extinct. But they didn't die because they were eaten. Although some of them did attack each other, but that was not the main reason all the dinosaurs extinct. So for the most part, yes, they were apex predators. And some of those dinosaurs were herbivores. But even though they were herbivores, they still were apex predators. All right, so go through this as click through the food chain image below and identify the thing that is in green. So you would have clicked on, and mine seems to be already highlighted, but if you, the word they're looking for is apex consumer. So that would be your owl. And then if we go to, yeah, mine is already highlighted. So hopefully you did yours as well. The primary consumer would be the grasshopper. The producer, and then why is it, I don't know why mine is doing that, but the thing that's highlighted in green is your producer. So I don't know why mine is saying incorrect, but the producer is in green. Okay. And this one to me is incorrect because your quaternary consumer should be the fourth thing in you. So we have four consumers listed here, primary, secondary, tertiary, and quaternary, but it has the snake highlighted here, and it should not be the snake. It should be your owl. So I don't know. I don't know why mine is already graded like this. But anyway, and your tertiary one should be the snake, and it is not the bird. All right, so ignore mine. I don't know why, and it won't clear. It doesn't start over for me. It just stays where it is. All right, maybe there you go. All right, so apex. Maybe I have to clear it each time. All right, I don't know why mine is going wacky, but make sure that you know if you're looking at this, which one is correct. All right, so before you go, you need to know these vocabulary words that are used in talking about a energy food chain and pyramid. Again, the whole reason for doing this is to talk about the flow of energy. All right, we're going to, and I'm going to give you an activity for that on Wednesday. All right, so now we're going to look at, and it is published. we want to look at the flow of nutrients in an ecosystem. And we're going to look at different cycles. All right. So now by nutrients, now we're looking at individual things that are needed for living things to survive, like water and carbon dioxide, oxygen, phosphorus, nitrogen. These are all called nutrients. So we're going to look at how they flow through an ecosystem. And so write this down, write this word down, biogeochemical cycles. And there are several of them. Okay, so here, and after you write that down, write this down right here, because these are the cycles that we're going to look at. The water cycle, oxygen, carbon, nitrogen, and phosphorus cycles. Now, one of the important things to remember again is it's called a cycle is because everything just keeps repeating over and over again. So nothing is lost. It just is moved from one phase to another or from one organism to another, but eventually the cycle starts all over again. All right, so we're going to look at these. He's going to start with the hydrologic cycle and the carbon cycles. Um,
Horrible story alert. So I was hanging out with my 2-year-old second cousin in the ocean in Florida, and we're jumping up and down with the waves, and it's fun. But then the water got all calm, and I said, "Oh, no more waves," because like that's the top tier communication I'm going for with a 2-year-old. But then he said, "Don't worry, there will be more," and I was like, "How do you know?" And he was like, "It's a cycle." Yes, it is a cycle. The Earth is filled with cycles.
I always have to slow him down. He talks too fast.
You should know it too. The universe is stuff that we've got on like every last particle of matter or calorie of energy has been around since the Big Bang. It just continues over and over again. And when it comes to matter, at least Earth is essentially a closed system. All matter gets passed around in biogeochemical cycles. The pathways for molecules like water or elements like carbon and nitrogen and phosphorus to move through all of the Earth's various ecological. Now, of course, we couldn't possibly talk about how all matter gets cycled around Earth in one video because it's big. Consider this an introduction to biogeochemical cycles, starring my two personal favorites, carbon one. I'm sure you already know about at least one kind of planet-wide recycling because it's the most obvious to us, a hydrologic cycle, which describes how water moves on, above, and below the surface of the Earth, driven by energy supplied by the sun. Talking about the hydrologic cycle, it's most useful to think about all the water on Earth being held in a series of reservoirs. The ocean, or the atmosphere in the form of clouds or in polar ice caps. So not only does water cycle through different places, it also takes different forms at different places in the cycle, liquid, solid, or gas. And since it's a cycle, there is no beginning and there is no end, so where we start our discussion is arbitrary, but we're going to start it off with precipitation. Rain, hail, snow, sleet, gravel, all that stuff is precipitation. It happens when water that's being held in the atmosphere condenses or turns from a gas into a liquid. Solid right out of the air. The opposite of condensation, of course, is evaporation. A liquid into a gas, and when a substance converts straight from a solid to a gas, that's sublimation, and when it's from a gas to a solid, that's deposition. And now you know. Back to condensation. It's responsible for the formation of clouds, which happens when vapor rises and cools or is compressed to the point that it can no longer be gas. At this point, the vapor forms droplets. This is the same thing you see happening on the glass of iced tea on a given day. The water in the air around the glass gets cold and turns from gas into vapor. So a cloud is just a big pile of condensed water droplets. In a sense, it's a gigantic floating reservoir. Clouds are a handy feature of the hydrologic cycle because then they drip from the landscape water around the globe, so water that evaporates over the ocean can be deposited else. Otherwise, if water always got deposited right where it evaporated, the precipitation would be almost all right over the ocean because that's where most of the evaporation takes place. So wind moves clouds, and as water keeps condensing, clouds getting heavier until our old friend gravity takes over and pulls the condensed droplets to the ground in the form of rain, or in the form of snow or hail or sleet or cloud. So now the water is on the ground, but gravity continues to work on it, pulling it toward its resting place, whatever that might be. It either pulls the water across the surface of the land for the lowest point, across what's called runoff, or it pulls it underground. Water can be trapped or stored for a little while in places like lakes and ponds and wetlands, but most of the water that falls as precipitation gets pulled lower and lower and lower as runoff through the creeks, streams, and rivers until it reaches the ocean. Some really cold places, water of course freezes and hangs around the edge of ice in certain places for thousands of years at a time, like poles and glaciers, mountain tops. But when it melts, most of it too runs off into the ocean. So you see where this is going. Right? Oceans are a big deal. They're pretty much the biggest deal. They're the reason that we have the hydrologic cycle in the first place. They're also the reason we have awesome stuff like weather and life on Earth. The weird thing about oceans, though, is that they're salty. And there is a reason for this. Water runs to the ocean, it erodes minerals like salt from soil and carries it to the ocean. Now, water heading to the ocean might not taste salty, but the salt's in there. But here's the thing, when the water evaporates again, the salt doesn't evaporate with it, it gets left behind. You keep this up for a few billion years with pure water evaporating from the ocean and then returning with tiny amounts of salt, and that's your recipe for a billion to fry. And all this shows that the world's oceans are literally the last stop for all the liquid water on Earth. The only way to get out of there is through evaporation, and that's all your minerals behind. Now, living things also have their role to play in the hydrologic cycle. And both plants and animals, the breakdown of carbohydrates produce energy, produce water as a waste product. So we lose water through evaporation from our skin. We also exhale water vapor, and of course we pee it out. Indeed, most organisms on Earth are made mostly of water, although that water cycles in and out of us pretty quickly. In plants, water is sucked up through the roots and moves up to the leaves, the gas exchange, where it evaporates quickly. This process is called evapotranspiration. Since there are so many plants here on Earth, it's responsible for the atmosphere. This process is essentially the opposite of condensation, in that it turns liquid water into gas. The energy of the sun drives evaporation, whether it's from the surface of the ocean or from treetops and leaves. And then once all that water evaporates into the atmosphere, we're right back where we started. It's a cycle. So now that you know a little bit about the hydrologic cycle, it's a little easier to understand how the carbon cycle works. Carbon.
All right, I'm going to pause it there so that we can actually look at the, all right, give me 1 second. You need to be able to look at a picture of let me just, I'm gonna do it this way rather than try to, okay. Now I'm sure you're probably used to, let me get a different one that looks more like this. Okay, let's look at it this way. So everything he just said, one, you all were used to it being called the water cycle. You also need to change your vocabulary to recognize that the hydrolytic cycle is your water cycle. Okay. He started, and you used to just the three: precipitation, evaporation, condensation. For environmental science, we've added a whole bunch of other words that you need to be familiar with. So again, lots of vocabulary. So precipitation is fairly simple. That's just the water falling from the clouds to the earth. It can fall in several different ways, so you need to remember that precipitation can be hail, sleet, snow, rain. So all of those are forms of precipitation. So again, we had a lot of precipitation last week, and why you had flooding, because we had a lot of runoff. So surface runoff. One of the issues why we have flooding is the runoff runs off into lakes. For us, lakes and streams, it doesn't go to the ocean, and there's a limit to those. So when those water levels rises, it was rising to the point where it was overtaking streets and taking down bridges in some places. So, but that's surface runoff. So it precipitates, it hits the land, and it can run off into a body of water. Notice if you follow those arrows, you also have it soaking into the soil. So the other issue, especially here, we have a lot of trees in Atlanta, and the issue that we have when it storms is the ground gets saturated with all this water. So infiltration is a vocabulary word you need to know. The water infiltrates the soil, makes it nice and soggy. And if the roots are not deep for these big trees, the tree falls over, it falls over on a power line, and there we have a little bitty storm, takes out the power because the ground is so saturated that the trees can't stand up anymore. Okay, so infiltration. Some of that water can go into a what we call a water table. So it goes deeper into the soil. Some of you have aquifers and wells, and wells get their water from underground water tables where the water soaked all the way through the soil. So again, follow with me with the arrows in the picture. So we've got precipitation, and we've got two things that can happen. It can infiltrate the soil, or it can run off into a body of water. The groundwater flow, again, we are stored in aquifers or wells or underground caverns of water. They can be taken up by the plants. So that's where we're cycling it back. It can be taken up by plants. Some of these underground water supplies will go back into a river or a stream. So that's where that one is saying discharge to streams. But it's also being taken up by these trees that are along the way because they absorb some of the water from the soil. All right, so that's our precipitation and what's happening on the ground as it's still liquid water. Then it can go back into the atmosphere by evaporation. So evaporation of the water from large bodies of water, but we also have a special name for when it leaves the plants. It's called transpiration. Okay, so notice all the places that water can evaporate from. It's going to evaporate from the lakes and streams and oceans. It's going to evaporate from the soil and from plants. But mostly with plants, we don't call it evaporation, we call it transpiration. So we perspire, plants transpire. Okay. Now, the thing that is not labeled in this diagram, at the top, the cloud should say condensation. And condensation means that you took this gas form of water, this water vapor, and then you made it liquid again. So you remember from your early science where you have the three stages of matter. It goes from water, liquid, solid, gas. In this cycle, we're not having a solid form, but we are going to have a gas form. But when it cools in the cloud, it becomes a liquid again. Okay, So we have a cycle of water that goes from precipitation to being absorbed by the soil, being run off into other bodies of water. And then that water is also, the groundwater is being absorbed by the plants so then they can transpire. It's being evaporated from large bodies of water, or it's being evaporated from the surface of animals. Okay, or we exhale water vapor. During respiration, we exhale water vapor. It goes into the atmosphere. Okay, so make sure you can understand a diagram like this. Sometimes you get a diagram that has no labels on it, and you need to be able to label all of the activity in the hydrologic cycle. Okay. Any questions about the hydrogen? This is probably the cycle you're most familiar with. So this one's a little easier than the ones that are going to follow. All right. I'm going to let Mr. Wonderful go ahead and talk about the next cycle, the carbon cycle. All right. So again, our nutrient that we were talking about there was water. All living things need water. And this is how it is cycled through our biosphere. All right, so he's going to talk about the carbon cycle now.
Is one of the most abundant elements in the universe, and here on Earth, it's always on the move, just like water jumping from one reservoir to the next. And that's a good thing, because A, all living things require carbon for their structure and to feed their bodies, and B, it's a big component in a bunch of non-living things as well. It's in rocks, in the ocean, trapped in ice, plus it's in the atmosphere, where it helps regulate the temperature. Without carbon dioxide, Earth would basically be a frozen wasteland. So lucky for us, there's a whole pantload of carbon out there, because we need it. So let's start out with the carbon in living. In order to take all of the water out of it, carbon would constitute about half of what would be dust that you see. The first biological carbon reservoir is a bunch of carbon dioxide out of the atmosphere because they needed to photosynthesize. But CO2 is also one of the byproducts of respiration, the process by which they use that energy. So plants take in carbon dioxide from the atmosphere in photosynthesis and then release CO2 back out into the atmosphere in the respiration process to make all their cellular functions. And right now, you're like, wait, no, isn't the deal that plants get to take in the carbon dioxide and animals get to breathe it out? Well, yes and no. It's just that plants take in more CO2 from the atmosphere than they give off through respiration. The rest is like their profit. It's what becomes the body of the plant. That's right. That's big old massive tree. All of that mass. Gas. Cool. So carbon absorbed by plants has three possible things. It can be inspired back into the atmosphere, it can be eaten by an animal, or it can be present when the plant dies. And if a tree falls in the right kind of forest and it's not allowed to decompose normally because a bunch of other plants all fell right on top of it and they died and get buried, squished together and form rocks like coal. We call these carbon-rich geological deposits fossil fuels. Lately, one of humanity's very favorite pastimes is digging up all of this old carbon in the form of coal and oil and natural gas and burning it to fuel our pretty much everything. But I'll get to that later. Another extremely important carbon reservoir is the ocean. Now, carbon dioxide dissolves really easily in water. Once it's in there, all of it's used by phytoplankton, tiny plant-like organisms that form the base of the marine food chain. They use carbon in photosynthesis, and they also use it to make calcium carbonate shells. And when these guys die, their shells settle to the bottom of the ocean, pile up, become compressed, and over time make rocks like limestone. Now, limestone obviously doesn't burn super well, so it's not considered a fossil fuel, but as limestone deposits are eroded by water, the calcium carbonate is broken down to eventually form, among other things, carbon dioxide and carbonic acid. We make lime and cement by heating limestone, which produces a pretty good amount of carbon dioxide. And when we do burn fossil fuels such as coal and petroleum products and natural gas, it also releases carbon in the form of carbon dioxide that's been stored for hundreds of millions of years in the geosphere, is just a fancy sciencey word for Earth rocks. This process is what started the atmospheric carbon dioxide levels rising like crazy in the past couple hundred years. And the excess of carbon dioxide in the atmosphere causes global climate change because CO2 in the atmosphere prevents some of the sun's energy from re-radiating back out into space. So yeah, our planet is getting warmer because we've been burning through this massive reservoir of carbon that we have locked underground. This is causing all kinds of problems that we can see already, and it's very likely going to keep causing bigger and bigger problems with time. And the situation could be helped a lot if we would just stop unlocking all that carbon and spitting it in the atmosphere, but in some respects we don't even have control of the situation anymore because of ice. Remember how I said that carbon is often trapped in ice? Well, places like Siberia and northern Canada and Alaska, cold places that also have plants, they contain huge carbon reserves that are trapped in permafrost, ground that's frozen year-round. These places are basically frozen wetlands that add another layer of dead plant matter each year. But as permafrost melts, these dead plants decompose, and huge amounts of carbon dioxide and methane are released into the atmosphere, creating a positive feedback loop. Our carbon-burning lifestyles unleashing this other huge carbon reservoir, which keep the whole greenhouse effect going with or without us. Just saying. Sorry to end on such a frightening and depressing note, but the stability of global climate is not as stable as we would like it to be, and the fact that we're throwing it out of whack is one of the most important reasons to study ecology in the first place.
All righty. So let's look at the graphics on, and I'm going to do the same thing. I'm just going to pull up, type in carbon cycle. I have a PowerPoint, but I don't want to waste time going through changing screens. All right, let's look at this one. All right, so again, you have a bunch of arrows and indicating that it is cycled. So we start in the atmosphere, and carbon dioxide is part of photosynthesis. So the first thing, so we'll start with the carbon dioxide in the air and go to the tree. So during photosynthesis, the equation is carbon dioxide plus water makes glucose and oxygen. So it is absorbed by the trees. And then, like he said, things decompose. The tree is eventually going to die. And some of that carbon that's stored in the tree will end up in the soil and be released that way. So then you have all these arrows going. One of the arrows will go towards returning it that way. The other thing is that carbon dioxide is exhaled. We exhale carbon dioxide, even though it's in the atmosphere. And when we inhale it, but we don't use it that way. We get our carbon from the things we eat. Okay, and then we exhale carbon dioxide. So animal respiration is how it gets back into the atmosphere. So that's a mini cycle right there all by itself. Other organic organisms can also give back carbon dioxide. Trees also do respiration. So again, we talked about they make their food, but then they use the food during respiration. So not only do they use the carbon dioxide, but during respiration, they give it off. So that's another cycle. All right, they should add an arrow down to the soil from that as well, because it is going to die and decompose. All right, then you have the factory. The factory is digging up fossil fuel, so the coal and the oil that they're digging up. And all the coal and the oil is what they call a carbon reservoir, this stored carbon. Okay, so when the factories burn these oils and coals, they are releasing the carbon that was stored there for thousands of years. The other thing, carbon emissions come from cars. So we use some of the fossil fuels to run our cars and other things powered by gasoline. And so that is another way that the carbon is returned to the cycle. Now, what he was also talking about in terms of global warming, one of the things that makes Earth a warm, inhabited planet is we have carbon dioxide in our atmosphere. And it's like the blanket around, we call it the blanket around the Earth. And it's a good thing. Other planets don't have this carbon in their atmosphere, if they have an atmosphere at all. And so they're not warm. And so we can't live there. We live here because carbon dioxide keeps our planet warm. What is happening is we are, this side of the diagram is we're burning it and using it in our cars more and more than the natural cycles. So in the natural cycle, you're taking it in and you're putting it back. You're taking it in, you're putting it back. However, with us burning fossil fuels, we're adding extra carbon dioxide back. So we're adding more carbon dioxide than is being removed. The other issue we have is we're cutting down all these trees. We're building all these houses, cutting down all the trees. So the thing that takes the carbon dioxide out of this cycle is not there. So the trees are not absorbing the carbon dioxide stays in the atmosphere. Then we go and burn some fossil fuels and we add some more carbon dioxide to the atmosphere and we thicken our blanket. So when the blanket gets thicker, the temperature gets warmer. Okay, so this is global warming, but we'll talk about global warming some more later. But right now you need to understand it as part of the carbon cycle. Okay, so again, carbon is our nutrient and it is cycled through plants because it is absorbed by plants. It is returned several ways. It is returned during respiration, and it's also returned when decomposers break down materials. It is returned to the atmosphere that way, or it is returned to the atmosphere when we burn fossil fuels. Okay, and then we start all over again, but it all starts with the trees. Okay? All right. Any questions about that? All right, so we got just a few minutes left. Let me come back over here. In the few minutes that are left, go through and look at these slides, the water cycle and the carbon cycle. And we'll do a review of them. And this one goes through the oxygen cycle. We didn't talk about that yet, but we will. But go through these slides in the few minutes that are left. And yes, just look at the water cycle and the carbon cycle. We'll do oxygen, nitrogen, and phosphorus on Wednesday. And again, look at the vocabulary words: runoff, infiltration, the usual words: precipitation, condensation, evaporation, transpiration, infiltration. A lot of vocabulary. Make sure that you are clear as to where all of these, if you were given a blank diagram, could you put all of these words in their proper place on a diagram? Same thing with the carbon cycle. If you were given a blank diagram, could you label all the parts of the carbon cycle?